Group theory is a foundation of mathematics. We study groups of order 2, 3, 4, and beyond, but usually in a single layer. In this video, I introduced dimensional group theory, a way to extend group structure into higher dimensions. We'll start with tiny groups you already know, then lift them into a new dimensional language. What is a group? A set with an operation satisfying four key properties. First, closure. If A and B are in the group, then a combined with B is also in the group. Second, associativity. It doesn't matter how you group the operations. A times B times C equals A times the quantity B times C. Third, there's an identity element E that leaves every element unchanged when combined. And fourth, every element has an inverse that cancels it out to give the identity. Let me show you two minimal examples. The group of order 2, that's Z mod 2 with elements 0 and 1 using addition modulo 2. Here's its operation table. The group of order 3, Z mod 3 with elements 0, 1, and 2 using addition modulo 3. Here's its table. Now, instead of stopping at these flat two-dimensional tables, we're going to take a leap from 2D tables to higher dimensions. Dimensional group theory. Instead of stopping at a flat two-dimensional table, we extend the idea. Groups can be represented as dimensional objects. Here's the key mapping. Binary operations give us 2D matrices, ternary operations give us 3D cubes or tensors, and n-ary operations give us n-dimensional hypercubes. Next, I'll show exactly how to build those 2D matrices and 3D tensors. 2D group of order 2. We choose an ordering, row equals 0, 1, and column equals 0, 1 transpose. Our row vector is 0, 1. Our column vector is 0, 1, written vertically. Now for the addition, column plus row. We take the column vector and add it to the row vector element-wise. 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and 1 plus 1 equals 2. This gives us the matrix with entries 0, 1, 1, 2. Applying mod 2, we get our final matrix 0, 1, 1, 0. For multiplication, column times row. Using the outer product, 0 times 0 equals 0, 0 times 1 equals 0, 1 times 0 equals 0, and 1 times 1 equals 1. This gives us the matrix 0, 0, 0, 1. 2D group of order 3. We use the ordering row equals open bracket 0, 1, 2, close bracket, column equals open bracket 0, 1, 2, close bracket transpose. Our row vector is open bracket 0, 1, 2, close bracket. Our column vector is 0, 1, 2, written vertically. To compute each cell, we use column plus row element-wise. The outer addition gives us 0 plus 0 equals 0, 0 plus 1 equals 1, 0 plus 2 equals 2 in the first row. 1 plus 0 equals 1, 1 plus 1 equals 2, 1 plus 2 equals 3 in the second row. 2 plus 0 equals 2, 2 plus 1 equals 3, 2 plus 2 equals 4 in the third row. This raw sum gives us the matrix with entries 0, 1, 2, 1, 2, 2, 3, 4. Now we apply mod 3 to each element. 0 stays 0, 1 stays 1, 2 stays 2. 1 stays 1, 2 stays 2, but 3 becomes 0. 2 stays 2, 3 becomes 0, and 4 becomes 1. Our final 3 by 3 matrix is complete. 3D group of order 2. Now we move to 3 dimensions. The rule is T of I j k equals A sub I plus B sub j plus C sub k mod 2. Our axes are row open bracket 0, 1 close bracket, column open bracket 0, 1 close bracket, depth open bracket 0, 1 close bracket. Let me compute all T of A, B, C entries systematically. T of 0, 0, 0 equals 0 plus 0 plus 0 equals 0, which is 0 mod 2. T of 0, 0, 1 equals 0 plus 0 plus 1 equals 1, which is 1 mod 2. T of 0, 1, 0 equals 0 plus 1 plus 0 equals 1, which is 1 mod 2. T of 0, 1, 1 equals 0 plus 1 plus 1 equals 2, which is 0 mod 2. T of 1, 0, 0 equals 1 plus 0 plus 0 equals 1, which is 1 mod 2. T of 1, 0, 1 equals 1 plus 0 plus 1 equals 2, which is 0 mod 2. T of 1, 1, 0 equals 1 plus 1 plus 0 equals 2, which is 0 mod 2. T of 1, 1, 1 equals 1 plus 1 plus 1 equals 3, which is 1 mod 2. Now let's organize these into 2 by 2 slices. For depth equals 0, where C equals 0, we have entries T of A, B, 0 equals A plus B plus 0. Before taking mod 2, this gives us 0, 1, 1, 2. After mod 2, we get 0, 1, 1, 0. For depth equals 1, where C equals 1, we have entries T of A, B, 1 equals A plus B plus 1. Before taking mod 2, this gives us 1, 2, 2, 3. After mod 2, we get 1, 0, 0, 1. So the full 2 by 2 by 2 tensor is two slices. The first slice is the matrix open parentheses 0, 1, 1, 0, close parentheses, and the second slice is the matrix open parentheses 1, 0, 0, 1, close parentheses. 3D group of order 3. Our rule is T of ij j k equals a sub I plus b sub j plus c sub k mod 3. The axes are row open bracket 0, 1, 2, close bracket, column open bracket 0, 1, 2, close bracket, depth open bracket 0, 1, 2, close bracket. I'll compute all 27 entries of T of A, B, C equals A plus B plus C mod 3, presenting them systematically, computing all 27 entries rapidly. Now let's organize these into three 3 by 3 slices. For depth equals 0, where C equals 0, we have T of A, B, 0 equals A plus B plus 0. This gives us the slice, 0, 1, 2 in the first row, 1, 2, 0 in the second row, and 2, 0, 1 in the third row. For depth equals 1, where C equals 1, we add 1 to every entry of the first slice, then take mod 3. Starting with 1, 2, 3, 2, 3, 1, 3, 1, 2, we apply mod 3 to get 1, 2, 0, 2, 0, 1, 0, 1, 2. For depth equals 2, where C equals 2, we add 2 to every entry of the first slice, then take mod 3. Starting with 2, 3, 4, 3, 4, 2, 4, 2, 2, 3, we apply mod 3 to get 2, 0, 1, 0, 1, 2, 1, 2, 0. The final 3 by 3 by 3 tensor consists of these three slices stacked together. Here's the complete generalization. If G is an ordered group with elements e sub 1 through e sub n, then for 2D m sub ij equals the operation of e sub I with e sub j. For 3D t sub ijk equals the three-area operation of e sub I, e sub j, and e sub k. For nd, h sub I1 through n equals the n-area operation of all corresponding elements. If the n-area operation is derived from a binary group operation star, then h sub I1 through n equals e sub I1 star, e sub I2 star, dot, 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 star, e sub n. And that's the complete picture. We took tiny groups you already know and showed how to lift them from flat tables to matrices, then to tensors, producing a dimensional ladder of algebraic objects. Each dimension reveals new structure while preserving the essential group properties.